Hello dear friends, welcome to my channel. Today's discussions is quantum mechanics. How are observable operator? Okay. In classical mechanics, an observable is a real valued function on the set of possible system states. Example, position and momentum. In quantum mechanics, an observable is an operator or gauge where the property of the quantum state can be determined by some sequence of operations. We have analyzed how particles are represented by gates in our Hilbert space, and taken a look at some of the mathematical involved in working with these gates. In this video, I want to move on the second half of our framework, how we represent physical quantities x, e, energy and momentum, position, energy and momentum. Okay, we posited that physical quantities are represented by linear operator in our Hilbert space. Now we are going to further develop this idea and formalize it in mathematics. We are going to change our language a bit. We are going to use the word observable for any physical quantities that we can measure out of our particle. Particle includes position, momentum, energy, and angular momentum, or combination of those. Basically anything we can measure and therefore observe from our particle. Before digging into the nuance of how we represent these observable operators, I want to remind ourselves about the formal definitions of linear operator, just to make sure we are on the same page. A linear operator is a map on a vector space that represented the linear structures of the space. In other words, a linear map satisfies the following properties. Addition is still addition, and scalar still scalar. Scalar multiplication is scalar multiplications. Okay, note that a linear operator is an abstract map, while a matrix is a representation of a linear operator in a particular basis. We will see in a bit that quantum mechanics has no standard basis, so that why you will almost always see us working with the abstract operations themselves. Moving back into quantum mechanics, we established that we suspect physical observables are represented by some linear operator in our space of gates. Given observable operators, how would we get the possible values that we can measure? Suppose 6.04 ev electrovolt, energy 0 point something, the energy values. Okay, so you see that 13.6 ev and 0.54 ev and minus 54.4 ev. Okay, energy. To begin solving this problem, let us look at angular momentum as an example. Okay, as an example, say we have a particular and an apparatus to measure angular momentum. This is the measures. Okay, we say we have a particular and apparatus to measure angular momentum. We can take a measurement and know that at this moment the particle has, okay, so at this moment the particle has a angular momentum of 1.41 newton per meter per second. Okay, newton meter second. So therefore at this very moment the particle has to be represented by a particular quantum state. That particular quantum state that corresponds to having that outcome of angular momentum. Okay, angular momentum. I mean, I think about the measurement told us what the angular momentum is. So we cannot be in a superposition of more than one outcome. Our particle has to be in the state representations this outcome. If instead our apparatus told us the particle had a angular momentum 2.44 a lot of, then the particle would be in a quantum state corresponding to that outcome. Hopefully you see that this would be true for any possible angular momentum we could measure. So what we have is a list of possible measured values and association Kate's representing states that 100% have. Okay, we just represent is as a Kate. That value we call the special states definite states. Okay, in these special states our particle has a definite 100% certain value for angular momentum, no ifs or buts. Now how would we get these lists from the angular momentum operator? Well, we have a list of definite angular momentum gates and associated values. I don't know about you, but to me this screams eigenvalue and eigenvectors, and this is the right direction to head. Okay, so you see eigenvalue and angular momentum and eigenvector. Okay, so this is eigenvalue and this is eigenvector, this is eigenvalue, this is eigenvector, and so on. Most textbooks just state this is as a fact, but hopefully you see why it is incredibly reasonable that eigenvectors show up. So let's summarize the conclusion. Every physical observable is represented capital E by some linear operator in this vector space. To figure out all the possible values of the observable, find the values E equals to E1, E2, E3. Okay, to figure out which states corresponding having that particular value, find the eigenvector and are corresponding to the eigenvalues. So this is the eigenvalue and corresponding eigenvector. These eigenvectors are called eigenstates and represent definite states that 100% have the value for the observable. This is the fundamental framework for how we represent observable in quantum mechanics. Now let's relate this to our current understanding to quantum states. Ever since the start of the series, we have wanted to represent our particle as a superposition. Okay, it is the superposition way of all possible of a measurement. So this is my coefficient and this is my possible outcomes. We now finally have to framework and language to do so. We now know that these outcomes states are actually the definite states of the observable, which are its eigenstates. So mathematically being it in a superposition of outcomes is done by being in a linear combinations of an observable eigenvectors. Now note that we haven't discussed how the coefficient relate to probability or what happens when we actually take the measurement. So we derive Born rule. Okay, I will create another video where I will show how to find out the coefficients with the help of this rule is called Born rule. Okay, we can use our physics in intuition to derive the mathematical properties that physical observable should have. First is observable need to have real eigenvalues. Intuitively, it does not make sense for a particle to have 2 plus 3i energy. Physical quantities are not inherently real. Number 2. Observable eigenstates must span the entire vector space. So span E1, E2 is equal to this form we can write. Remember that the span of a set of vectors is the subspace formed by the possible linear combination of these vectors. So this property says that linear combinations of an observable eigenstates cover the entire quantum vector space. Another way to word this is that any quantum state can be written as a linear combinations of eigenstate. This property actually is not that hard to prove. See if you can do it by considering what it physically means for a particle to lie outside the eigenstates. Eigenstate span. Give it a shot. The key is to realize that every single particle has a value for an observable, meaning if every particle has same value for position, for momentum and for energy, etc. So for example, x is equal to 6.6 meter or p is equal to 4.1 Newton per second. Okay, there are not any particles that have a position of none. Taking that idea, let's imagine that the energy eigen vectors did not span the entire. Okay, this is my inside span and this is my outside span. So inside span you can see this is my kits and outside span you see that this is not the linear combinations, no possibly energy measurement outcomes. So this would imply that was some quantum state outside the span and therefore could not be written as a superposition of the energy eigenstates. So this quantum state has no possible energy measurement outcomes, since remember that the eigenstates represent the definite states you get from a measurement, and this quantum state cannot be written in terms of any, but this is not possible. The particle has to have some value of energy when we measure it. Thus, it must be in some superposition of the energy eigenstates. This must also be true of every other observable we can measure. Therefore, the eigenstates of an observable must span the entire space. Lastly, we can actually conclude that eigenstates must be orthogonal, that is perpendicular. We can use the arrows analogy to see why this is true. Okay, here we have non-orthogonal states L1 and L2. Since they are not orthogonal, we can decompose L1 into two components. One component along L2 and some orthogonal component. Yet here we have that the L1 state contains a superposition of the L2 state, meaning there a chance we could get L2 if we took a measurement. This does not make any sense and goes against how we find states. Therefore, the eigenstates from an observable must be mutually orthogonal. So friends, I hope that you can understand whatever I want to say. I want to say span the entire vector space mutually orthogonal. Each states can be normalized, and observable eigenstates must form an orthonormal eigenbasis. So friends, thanks for watching, and I hope that I can give you some idea that what is observable operator. It is also called gauge, okay, in quantum mechanics. Yeah, so you will get it everything in the Googles, okay, Googles, that quantum mechanics in quantum observable manifest as self-adjoint operator or separable complex Hilbert space representing quantum state space. Okay, Hilbert space I have already discussed in my video that we used it in Kates. Okay, in the case of transformations laws in quantum mechanics, the requisites automorphisms are unitary linear transformation of the Hilbert space V. Under Galilean relativity, special relativity, the mathematics of frames of reference, restricting the set of physical meaningful observable. In quantum mechanics, measurements of observable exhibit some seemingly unintuitive properties. Specifically, if a system is a state described by a vector in a Hilbert space, the measurement process affects the state in a non-deterministic but statistically predictable way. Okay, thanks for watching. I hope I can clear, I can give some idea. And Born rule I will discuss. Okay, that is very important. The probability, we find out probability.